Hello and welcome. I've been working on a Moon Patrol clone game for the CoCo, and most recently I added a swarm of aliens that come and swarm around, but they're getting massacred. They need a way to defend themselves, and our player needs some kind of a challenge. I'd like them to shoot back, and to do so randomly. And a while back, Glenn Hewlett posted to the CoCo Discord a very simple routine to generate pseudo-random numbers that was generated for him by AI. It's in 6809 assembly, and I've been meaning to go through it to see how it works. Every day I would flip a coin, waiting for it to come up heads to tell me that today's the day. Well, finally, it came up heads today, and today's the day. We're going to look at the code and see how it works. We will pit it against the CoCo Basic ROM's random function in a knockdown, drag out, no holds barred showdown. We'll analyze some experimental changes we could make to the AI generated code. We'll visualize how the code works step by step. And finally, if you make it to the end, for your reward, we will discuss nested fractions. Here's the code our AI overlord generated for us. We have this seed kind of thing, a couple conditional branches, we're doing a shift, we're doing an exclusive OR, and you can actually ignore all of this stuff. This is about adjusting the range of the output, but if we just want stuff between 0 and 255, this won't even get executed. And that's about it. Very little code, very few cycles. Not a lot going on. We'll dive into this in detail line by line, but first let's get a feel for how well this performs. Here's an assembly language app that helps us compare visually how different random number generator algorithms work. You can find a link to the code in the description. What it does is it will run that code to generate a random number from 0 to 255. It'll tell us what it returned. And this region over here is kind of a whole series of counters. You've got 32 characters going across with 8 rows of those 32 characters. So that of course gives us 256 slots. And each of these slots acts like a counter. And if you look really closely, you'll see that they're not all @ signs. There's one capital A over here. And that just so happens to appear at offset 29. So if our offsets over here start at 0, this is offset 29. And if the value of all of these in memory is 0, this is a value of 1. This is VDG character 1, and these are all 0. So what it's doing is each time a random number is selected, we offset into this area and simply increment that byte in memory. And in this way, we can kind of visually see which numbers get selected and in which order. So if I start stepping through, you'll see we get some A's distributed here and there. And if I let it fly, you'll see they appear fairly random. It's hard to find a pattern. But you'll probably start noticing that it's an extremely fair algorithm. So for example, if I stop it here, we had a bunch of Q's and they were being turned into R's. You'll see that everyone gets to be an R before we pick our first S. It looks like everyone got to be an R except the very first character. Now that's an R. And only now do we start doing the S's. So if we speed it up, we can start to see what this looks like visually. If you want your pseudo-random number generator to be unpredictable, this isn't quite that. At first it kind of seemed like it was just all over the place. But there's probably a very clear pattern if we look hard enough. And if we keep track of which numbers get selected, we can end up being very confident that the unselected numbers will become more and more likely to be chosen. Now let's see how that compares with the random function that's in the color basic ROM. What you're seeing here is the same app. The only difference is that it's using the color basic random number generator rather than that AI written simplistic random number generator. And pretty quickly we can see that it's radically different. This does not have that absolutely perfectly evenly distributed probability of each possible number from 0 to 255 getting selected. But it certainly is a whole lot more unpredictable. Now, I've been showing these kind of sped up so that you could see the pattern, but what would the speed difference be between these two algorithms if I just played them at their normal rate? So here we have both algorithms running side by side. On the left, we have that simple AI-generated algorithm with just a few instructions. And on the right, we have whatever it is the CoCo basic ROM is doing in its random number generator. One thing that becomes apparent very quickly is that in the CoCo basic ROM, if you look at all of those counters, those character counters, it's a mess. There is no order to them at all. So we are really just choosing random numbers with very little pattern, very little sense of being fair and making sure that everyone gets their turn. Whereas on the left, it is so orderly. Like everyone gets to be an A, and then everyone gets to be a B, and then everyone gets to be a C. The other thing is to just see how quickly does it seem like anything changes. Like on the left, how quickly are counters changing? On the left, it looks like we make our way through the entire buffer in just like a second or so. But on the right, it does seem like we're going a lot slower. In fact, if you took a look at the kind of average counter value on the left and the right, it's a bit harder to gauge on the right because they're so different. But the left does seem to be much further ahead. All right, let's speed them both up just using some video magic at the exact same rate, and let's see if it becomes even more apparent after we do that. It's a rather obvious visual giveaway when the left inverts everything so that the background and foreground colors of the characters are all inverted from what they were before, so far before the right even starts to do that. So how does this simple AI-generated random number generator work? The heart of this algorithm is really these two instructions, shifting it left and EORing with this magic number. But let's pop out a bit and talk about what a seed will do. The seed is 1 byte of storage, and we always fill it out with whatever random number just got generated. So the seed then gets used to generate the next number. Before this is ever called, we can initialize this random seed to be whatever we want. On startup, I just initialize it to 0. So this random seed gets used in conjunction with these instructions that twiddle around the bits to generate something that appears unpredictable. I should mention I did change some of the comments and some of the label names to something that makes more sense to me from what the AI generated, but basically this is what it generated. We grab the last random number we had in B, and for some reason if it's 0, we skip that shift and we skip these conditional branches. So if it's 0, we just immediately do the EOR. Otherwise, we shift left, filling the rightmost bit with 0, and we check if it's 0 again. If so, we're done. We don't do the EOR. If it's non-zero, we take a look at the carry bit. As a reminder, arithmetic shift left will take the 7th bit, or the leftmost most significant bit, and shift that into the carry. So here we're asking if that carry bit is clear, meaning the leftmost bit of B was clear. And if so, again, we will skip the EOR. But if we're lucky enough to do the EOR, we do so. And then in all cases, we remember the random seed. For now, this is a no-op, since we're only getting values between 0 and 255. And we're done. So what's with all of this weird stuff? Special case for 0, special case for 0 after we shift, special case for a cleared carry bit after we shift. Sometimes we do the EOR, sometimes we don't. Sometimes we do the shift, sometimes we don't. Sometimes we do these conditional branches that ask if sometimes we should do the EOR or not, but not always do we do the things that ask us if we should sometimes do the E. So why? What is all of this stuff? Well, like a medical researcher who figures out what things do by removing organs randomly from the patient and then seeing what goes wrong, let's just get rid of all the instructions I don't understand. Let's just always shift and always do the EOR. What could go wrong? Well, let's just step through this for a while. Seems like we're just... Oops. We were fine. But it looks like we converge on returning 11 as our random number. And so we just keep incrementing, of course, our character counter sitting at offset 11. So it gets stuck. So I guess those things were pretty helpful. So as you can guess, there must be something rather special about 11. If we run these operations on 11, let's take 11. First, we would shift it to the left. Actually, let's make sure we're in byte mode first. So if we do an arithmetic shift to the left by 1 byte, by 1 bit rather, we go from 1011 to 10110. And of course, shifting left just multiplies by 2, so we're at 22. Then we exclusive OR with 1D. And that brings us right back to 11. But still, surely this can't really be all that useful. I bet if I add it back, there won't be any difference. We're not going to improve anything. Checking whether the carry is clear after the shift. I mean, come on, who cares? This will have no effect. So we're stepping along. Well, it did seem to have an effect. We're definitely not getting stuck at 11 anymore, but now we're stuck at 0. And just a moments of thought makes that kind of clear. If our seed starts us off at 0, we shift to left, we're still at 0, and the carry is clear, so we're going to skip the EOR and just return 0. So as far as I can tell, this is just foolishness. This is really the thing. 0 is our special case. Although I guess 11 also is our special case. So let's check if it's 0 first, and then let's do this. Maybe this is enough. This should be enough. And here is my awesome simplified version of the AI simple algorithm, which, gets stuck at 11 again. Boy, sometimes I guess it pays to actually think about what you're doing before you do it. And sure enough, the only thing preventing that 11 from doing damage was this. Otherwise, we get stuck where we do that shift and we do that EOR, and then we end up with 11 again. So we got to protect ourselves against 0, we got to protect ourselves against 11, and presumably there are other numbers where if we got there, we would get stuck as well. Or are there? I wrote some simple Java code to actually test that out. For each possible starting seed, how long does it take? How many iterations does it take through this algorithm to hit 11 and get stuck? Or do we just never hit 11 for certain seeds? And sure enough, no matter what seed we start from, it always takes 8 or fewer iterations before we get to 11 and get stuck forever. And in fact, the pattern is kind of weird. 8785, 8786, 8780, 8786, 8785, 8786, 8784, 8786, 8785. There's a lot of math going on I don't understand. So let's take a step back and see exactly what this is doing. Let's walk through the algorithm step by step. At the very top, we'll have our input seed, which we're starting off at 0. In the middle, we have our magic number, which never changes. It's just always this weird sequence of bits. And at the bottom, we'll see the random number that gets generated as a result, and which will become our new seed for the next iteration. When we start off with 0, that's just the special case which says we're not going to do any shifting. We're just going to EOR it with the magic number, and then that will be our answer. In the next iteration, we take what's at the bottom and move it to the top. That's our new seed. We shift it to the left. And in here, this is the carry bit. So the very leftmost bit that was a 0 gets moved into here. When we shift to 0 here, that is our signal that we're not going to do the EOR. we're just going to take this as our final answer. So we copy that down to the bottom, and that's our answer. For the next iteration, we move the bottom to the top. We shift again. Again, we have a 0 in the carry bit, so we're just going to return that. For the next iteration, we take the bottom to the top. We shift again. We get a 0. That'll be our answer. For the next iteration, we move the seed to the top again. We shift again. This time we've got a 1, so finally we can do an EOR. And as you may recall, when you EOR two numbers, when the bits are different, you get a 1, and when the bits are the same, you get a 0. And that's the result of the EOR. For the next iteration, we copy that to the top. Shift to the left, 1 means an EOR, we do an EOR. Next iteration, we move that to the top. Shift to the left, 1 means an EOR, we do an EOR. For the next iteration, we copy the seed to the top, shift to the left. Now we've got a 0, no EOR, that's just going to be our final answer. So you may have noticed, every time we do a shift, we always end up with a 0 in this spot, and the magic number never changes, so we always have a 1 in this spot. That means that when we EOR the seed with the magic number, we're always going to get a 1 here, which would make the new seed always odd. And that gives us a bit of insight into why we're actually looking at this carry bit to decide whether to do that EOR. About half the time the carry bit will be 0, we won't do the EOR, and we'll end up with an even number. The other half of the time, the carry bit will be 1, we'll be forced to do the EOR between a 0 and a 1, and we'll end up with a 1 here, and it'll be odd. So not only are we protecting against these infinite 11 cycles, we're also trying to balance out the even numbers and the odd numbers we get. And the magic number is pretty carefully chosen so that we get a good, decent mix of bits. The idea is to add enough chaos so that as we go from iteration to iteration, we avoid cycles as much as possible. In fact, this algorithm ensures that the cycle will last 256 iterations, the maximum amount of time you can for an 8-bit number. I'm sure there's plenty of math that went into this that I don't understand, but I can accept that everything in here is necessary. And that just leaves one last thing. So far, we've only been using numbers from 0 to 255. This subroutine assumes that the caller pushed onto the stack whatever max they want for the range. And so far, the max has just been 255. So all we've been doing is we've been grabbing 255, putting it in the A register, comparing it with 255, concluding they're equal, and then skipping this stuff here, just returning. But what if the caller wants the result to be in the range from 0 to 7? In that case, the caller will be pushing 7 onto the stack instead of 255. So if the caller pushes 7, we do these 3 mysterious operations. We add 1 to that 7, so we get an 8. We multiply that 8 with whatever random number just got generated. That's still in our B register. So we multiply the max of the range plus 1 times the random number that was created, and then we take the high byte of that multiplication and move that to B, which is where the caller expects the result to be. Why would multiplying the max plus 1 times the result and taking only the high byte limit the result into the range that we want? I originally assumed this was maybe some fancy way of doing mod, because usually when you want a number that's in a large range to be reduced to a small range, you just mod it by that smaller range and then it will automatically be there. But the more I studied this, the more I realized this is not doing mod at all. So here we've got 256 possible slots for our random number. And imagine that instead of getting a result from 0 to 255, we want to calculate a result from 0 to 7. That's 8 possible results, so we divide all of these 256 squares into 8 groups. So now you can think about it like this. Whatever number gets chosen, let's say this one over here, we just look at whatever group it's in, and that's the number we'll return. In this case, we got 0, 1, 2, 3, 4. So we would just return 4 for this number. And in that way, we'll definitely return some number between 0 and 7, roughly balanced out to be even among the possible results. So let's take a look at the math. Let's make believe we picked the number 121, and we want to somehow get that in the range from 0 to 7. Each of these 8 groups contains 32 cells. So if we took our 121 and divided it by 32, that would tell us which cell it belongs to. And that's all we're really doing. But we're doing it in a kind of fancy way. We got the number 32 by counting how many cells are in each of those groups. And the way we did that is by taking the full number and dividing it by the number of groups. 256 slots total divided by 8 groups means that we have 32 slots in each group. So really, we're doing this. But when you take a number and divide it by a fraction, that's the same as multiplying the number by the inverse of the fraction. So really, this is just this. And we can write that slightly differently by just putting the 121 in the numerator. And lo and behold, that's exactly what we're doing. We're taking the result, we're multiplying it by our max plus 1, and then by dividing by 256, we're grabbing the high byte. This is exactly this. Super slick. Now you might be thinking, well, come on, you're picking numbers that kind of work nicely. 8 evenly divides into 256. What if we wanted our max to be 6, so that the max plus 1 ended up being 7? How would this work? We're going to rerun the simple Eeyore algorithm, but we're going to say that the range that the result has to be in is 0 to 6. So it's going to do all that stuff. It's going to first find a result in the range from 0 to 255. It's going to multiply the answer by 7, which is our max plus 1, and then take the high byte to divide by 256. Our first result ends up being 0, then 1, then 3, then 6, then 5, then 3, then 0. Let's let it go. And it's looking pretty random. In fact, maybe even more random than before. It's no longer this perfectly fair algorithm where everyone has to be incremented up to one value before any of them can be incremented to the next one. We're just about done, but I would be remiss in not mentioning that typically people will try to seed the random number generator with an unpredictable number. I've just been seeding it with 0, and that's silly. A common way people will seed the random number generator in BASIC is to use the timer function. Or you could do as Donkey King does, and seed it by counting how many cycles through a loop you can make before the user responds to a user prompt. Because this AI-generated code is so orderly, I will not be using it in any cryptographically secure applications anytime soon. But it should be fine for my game. Next time, the CoCo Basic ROM's random function gets the same treatment. We will explore how it works piece by piece. We'll understand how it is so doggone random, and why it is so doggone slow. If you'd like a hint as to why, the answer is floating in front of you. Do you get the point?